I welcome you all to the Spark Research YouTube channel. This is Dr. Vijendra, Assistant Professor in the Department of ECE. So this is the another session for this course, Analog and Digital Communication. And this is the last part of this unit second, that is the radio transmitters and receiver. So in this session, we are going to take the contents from this unit second only. And we will talk about the FM transmitter, that is the direct and indirect method, FM super heterodyne receiver, noise in FM, and the need for pre-emphasis and de-emphasis circuits. So let's go. Now let's talk about the first FM transmitter. So if you remember about the FM modulations, so here what to do, how can we design these transmitter circuits for FM or AM. So in the previous session we discussed like FM AM transmitter, where we are using the the AM modulation with the amplifier. So same things here we are going to do. We will have the FM type of the modulation technique, and then we'll have the amplifier, right? So first of all, this is the the indirect type of the FM transmitter. So here you can see what is this mt is your message signal, so integration over this m of t. So we'll have the information, and then there is a crystal, so which will generate the carrier wave, right? So after generating the carrier wave, we'll have the phase shift by pi by 2, and then use this DSBC modulator. So finally we'll have the frequency modulated signal, right? So this is your indirect transmitter. So once we'll have the signals, then we'll use this frequency multiplier. Here we'll use the del of f is equal to 25 hertz, and that will shift your frequency. So initially you will shift fc1 will be 200 kilohertz. Again now after shifting by another del of t is equal to 1.6 kilohertz, you will have fc2 is equal to 12.8 megahertz. And again you will have the local oscillator, which may generate the signals in the range of the 10.9 megahertz. So with the help of the frequency converter and the deviation, again the third deviation may be in the 1.6 kilohertz, you will have the fc3 is equal to 1.9 kilohertz. Finally we'll use this multiplier, frequency multiplier, by 48, and then del of f4 will be 76.8, and finally we'll get the final carrier signal of your modulated signal, which we are going to amplify and then send, right? So this is the transmitter for your FM type of the amplifier. So here the simplified diagram for this commercial FM transmitter using the Armstrong method is there. So the final output is required to have a carrier frequency of 91.2 megahertz, and with the del of f is equal to 75 kilohertz. So we can begin with the NBFM, that is narrow band frequency modulation, with the carrier frequency of Fc is equal to 200 kilohertz generated by a crystal, right? So this frequency is chosen because it is easy to construct a stable crystal, right? That is why we are choosing it, right? And the deviation we are choosing of 25 hertz initially, right? And because beta we have to maintain it less than 1. Why? Because the NPFM must have the very less beta, otherwise it will have the higher the band width. In that case it will not be the NBFM, it will becomes the WBFM, that is wide band frequency modulation. Similarly we can shifting the finally will shift your frequency at the the final frequency shifting will be fc4 we will receive, that is 1.9 into 48, that is 91.2 megahertz. Clear? So this is the the summary here, simplified block diagram of your Armstrong indirect wave generator. So in that case, sometime if you need to draw the block diagram for indirect method of this FM transmitter, in that case you can use this block diagram as well, that is 1 and BFM along with the frequency multiplier, right? So the previous slide and this slide both are same only, this is the shortcut. Okay, so now let's talk about the direct method. So the previous slide we discussed, that was the indirect method. Now we are going to talk about the direct method. So in this technique, we will not use the frequency multiplier, we will use the VCO, that is voltage controlled oscillator, right? So first of all, we'll have the information, then audio amplifier, then pre-emphasis circuit, and then we will use the VCO. So how exactly we can achieve the frequency modulated here? So f of IET, that is the instantaneous frequency, will be equal to the f of C plus k of f MMT. So this is a carrier wave frequency, and then this is the which will vary according to the masses information. So in a voltage controlled oscillator, that is VCO, this is the main part of this transmitter, right? So the frequency is controlled by an external voltage, right? So the oscillation frequency varies linearly with the control voltage. So this is the major cracks of this VCO. So here your voltage, the voltage will manipulate your frequency. So that is the main crux. So we can generate FM by using this modulated signal MT as a control signal. So this will gives this is your instantaneous frequency, which will be equal to the carrier frequency and plus like your KFFMT. So clearly you can observe that instantaneous frequency is depending on the both your carrier frequency and definitely the masses signal. So that leads to the frequency modulation. So one can construct a VCO using an either operational amplifier and a hysteresis comparator. Another way to accomplish the same goal where the one of the reactive parameters, that is C or L of the resonant circuit of the oscillator. We can use the Colpitts type of oscillator also to vary it. So let's suppose the Colpitts type of oscillator, so where omega naught can be find 1 by square root of omega LC, right? So here L and C is the variable parameter. So with respect to L and C, we can vary the amplitude, and correspondingly we can vary the frequency, right? So let's see how can we vary in the C, that is capacitance. So let's suppose C is equal to C naught and minus of K and MT. So this is the masses signal, right? So capacitance will vary according to the masses signal. In that case, just replace your C in order to obtain the resonance frequency, right? So here 1 over a square root of L of C, just replace it, and you can expand it using the binomial expansion. So first term you can keep it and the remaining terms you can neglect, because K of MT divided by C naught is very less than 1. So you can neglect other higher terms, and finally your omega naught will be omega C plus K of M into MET, right? So because C is equal to C naught minus K of MT, that we have already the mentioned in the beginning here. So the maximum capacitance deviation we can find, that is del of C, that is C minus C naught, is equal to del of C divided by C naught is equal to twice K of F MP divided by omega C, right? So twice of del F divided by del C. This will give you the maximum deviation. So in practice, del F by Fc is usually small, and hence del C is a small fraction of C naught, which helps limit the harmonic distortion and rises because of the approximation used in the derivation. Apart from this, the variation in the C, you can also vary in the inductance, where the inductance of a coil is varied by a current through the second coil, right? This results a variable inductance whose inductance is proportional to the current in the second coil, right? So that is also possible using the saturable core reactor. Okay. Okay, so now let's continue to talk about the FM receiver now, that is the transmitter. Whatever we have discussed, that is both indirect and direct wave. So indirect we are using the multiplier, and indirect we are using the VCO, that is voltage control oscillator. So FM super heterodyne receiver is almost very similar to the AM super heterodyne receiver that we have already discussed in our previous slide. If you did not visit it, I'll drop the link here in the description section. You can find it and you can visit that video also, right? So major thing is that in super heterodyne receiver, what is that? Here is your receiver, your RF stage, that RF tuning filter stage, so radio frequency filter stage, right? And then local oscillator and mixer is there, and then you will have the intermediate amplifier, then limiter, then the modulation, and then again amplify, right? So antenna and RF amplifier will capture and amplifies weak FM signals while filtering out unwanted frequencies using these RF states, right? Then local oscillator generates variable frequency signals that mixes with the incoming signal, that is coming incoming from the RF signals. So mixer will combines the RF signal and LO signals, right, and producing sum and difference frequencies. The difference frequency 10.7 megahertz IF is selected for further processing. So this is the difference, right? So in case of FM super heterodyne, we will use IF frequency of 10.7 megahertz, and in case of AM, if you remember, that frequency IF frequency is 455 kilohertz. So this is the major difference, right? So IF frequency and filter amplifies the fixed 10.7 megahertz IF signal with the high gain and selectivity. So limiter will removes the unwanted amplitude variations, that is noise, while preserving frequency modulated information. And FM demodulator, that is the the regular job that will convert the frequency variation in IF signal back to the original signal, right? And then finally amplifier is there. Okay, so here is some comparison of AM and FM super heterodyne receiver. So AM may have the highly affected by noise. FM definitely will be less affected by the noise. So IF frequency is different. For AM it is 455 kilohertz. For FM it is 10.7 megahertz. And for AM bandwidth is less, almost 10 kilohertz, and for FM bandwidth will be high, almost 200 kilohertz, right? So detector like envelope detector is being used here in AM, and in case of FM we'll use the phase locked loop or radio detector, right? And so amplitude variation carry the information in case of amplitude modulation, and here definitely not in case of FM, right? And cost is comparatively lower in case of AM. Now let's talk about the noise. So what is the fundamental difference between AM and FM? So AM masses information contains in the amplitude, right? And if it is amplitude, definitely there is a high chances to aid the noise, because noise is mostly available in terms of the amplitude. So additive noise like additive white Gaussian noise corrupts directly the modulated signal. And FM masses information contains in the signal frequency. The effect of noise in an FM signal is determined by the extent to which it changes the frequency of the modulated signal, right? So here we can see that instantaneous frequency of the input signal, that is Fi is equal to Fc plus K of Mt. This is original signal, and if noise is there, then definitely it will have the plus of n of Ct and then cos omega Ct and minus n of S Nt. So these terms will added because of the noise, and that will leads to the noise in case of your signal. And definitely the PSD, that is power spectral density, will also change because of the noise present. So effects in the noise in FM, you can see here, definitely in the case of higher frequency, you can observe the higher noise. And if we need good SNR, means higher SNR, signal to noise ratio, in order to detect the or recover the information. We'll use how to remove these challenges. So we'll use the pre-emphasis and de-emphasis in order to receive the original signal perfectly, right? So that will results to the improved SNR. So what are the major effects? Noise mainly affects frequency, not amplitude. Noise dominates at higher frequencies, so noise power at the output of an FM detector increases with frequency. And threshold effect, FM exhibits a threshold phenomena. So the below this threshold, the output SNR drops abruptly, and improve the SNR. That is the advantage of FM advantage, right? FM provides better SNR compared to the amplitude modulation. Okay, so now let's talk about the pre-emphasis and de-emphasis. So this is the circuits are basically RC type of the circuits which is being used in transmitter and receiver both, right? So in case of signal transmission without emphasis, like suppose audio signal is there, and then if you are transmitting now, you will have the very noisy signal, right? But high frequency loss, like, and if you are using the noise in pre-emphasis, then what will happen, your pre-emphasis circuit is there that will boost the high frequency signal, and then if you are used to sending it through the transmission channel, you will able to get the very clear and balanced signal. And so here improved audio quality, better SNR. So this is the advantage of the pre-emphasis and de-emphasis circuits, right? So in case of without pre-emphasis, de-emphasis, if we'll do, then we'll detect the noise and interference and poor signal to noise ratio. And in case of if we are using the pre-emphasis in the transmitter side, de-emphasis in the receiver side, that will result to the very good SNR of your received or recovered signal, right? So this is the advantage. Now let's see how to design. So pre-emphasis is the technique in which high frequency components of the modulated signal are artificially boosted before transmission, right? And why is it so? Since noise affects the higher frequency mode. And how to do? We'll use the RC type of the circuits. We'll see in the upcoming slides. De-emphasis circuit means your de-emphasis is the process of attenuating high frequency components at the receiver. And what why to use? To restore the original signal shape. Again we'll use the RC circuits, right? So let's see now. This is the typical pre-emphasis circuit. So here you can see RC is there, resistance, capacitance, and R is there, and so modulated signal and the DFM demodulator. In between that, in the transmitter we are going to use this pre-emphasis circuit, which is nothing. Basically this is a one of the high pass filter. You can see here high signal more than, if the frequency is having more than 30 kilohertz, it will pass through it, and if it is lesser, definitely will it will suppress, right? So and similarly this is your de-emphasis circuit. So this is nothing, this is your almost similar to the low pass filter here. So in input signals, the recovered signal, and then demodulation, and then use this de-emphasis circuit, low pass filter here. So whatever the signal that you wanted to recover, it must have the less than 2122, that is 2122 hertz, right? If it is higher than that, you may not able to receive the message. Clear? So here some more detail about the pre-emphasis and de-emphasis circuits. So your MSC signal is there, pre-emphasis circuit is there, and then transmitter. And so that's all in the transmission and the receiver, FM receiver, and then de-emphasis, and you will have the final message signal. So this is a PST, that is power spectral density of your typical, the pre-emphasis signals. So this is the circuit. Again we have already saw the circuits, and correspondingly this is your transfer function. So you can find the transfer function of these circuits for your pre-emphasis and de-emphasis. This is the transfer function, right? So transfer function h of f h of p of f is equal to 1 plus omega j, and divided by 1 plus of j omega 2, right? So this is the omega 1 is equal to 1 by f1, and omega 2 is 1 by f2. So this is the Fourier transform transfer function of your pre-emphasis circuit, and here is transfer function of your de-emphasis circuit. Okay, so that's all in this session, and we'll come with some questions. If you have any doubts, please drop your comments. Thank you to join the session.